Hi, friends of the sun. Welcome to our weekly reading group happening every Monday. And we just do this on Zoom, right? So you can join yourselves if you want. All the information for that is down in the description. And we usually have just an author of a paper that I found interesting join us here and discuss and present their paper for us. And today we have Heli from Weizmann Institute, and she's talking about D-Flow, which I think is a particularly interesting one. So let's go.
So hi, everyone. Thank you for coming. Today we're going to talk about D-Flow, as Hannes already said. I'm Heli, and I am a PhD student at the Weizmann Institute. I'm a student of Professor Yaron Liebman, and this work was done during my internship at Meta with this wonderful set of people. And we just got accepted to ICML, which is also exciting. So I guess we can begin. Can you see my cursor? Because you cannot.
Nope.
Yeah, there's something weird about the share screen. I mean,
Yeah.
I cannot see my cursor as well. So like, I don't know where it is. I cannot even stop sharing. Yeah.
Yeah, if you ever need it, you can also just go out of presentation mode and then put your
Yeah.
cursor wherever you
Okay,
want.
so I'm gonna try to to manage without it. I can't also move the the video.
Yeah.
So okay, hope we'll manage. Okay, so D-Flow. What we're going to talk about today is a framework for control generation from a given trained flow model. And we're going to start with a quick motivation. Why do we want to control our output of a generative model? And we'll go along. So generally, the motivation starts from an inverse problem point of view. And let's define what an inverse problem is. What is the setting that we're in currently? So the setting in inverse problems is that we have an observation, we denote as Y, and it can be all sort of some corrupted signal or missing information signal. In this case, what we see is we have an in-painted image. We have this bare image, and we have those missing pixels in our image, and that's our observation of the signal. And the model is and what we assume typically is that we know the forward operator that was applied to our original signal X that created this observation. So in this case, it would be a mask, as shown here. And in some cases, we also assume that there is some additive noise that is added to our observation. Okay, now our goal is to find a good X, a good model that explains our observation Y. And now, what is good? I mean, good is not something that we can work with, but let's see some examples. Here we have some suggestions of completions of these in-painted image. And I think you will all agree that the ones that are on the diagonal are not good X's that explain Y, and the ones that are off the diagonal are good ones. So in a sense, we have some prior on what we consider as a good X. And formulating this in a more rigorous way, we can say that we want to find an indistribution X that explains our Y. And this indistribution, in this case, would be the distribution of natural images, for example. So now, and the question is, how do we now take this indistribution notion and define it mathematically? So this is the part where generative models come in, which are the main tool that we use today to model distributions of some data types. So the general scheme of generative modeling is that we have our data distribution, which we denote here as Q. In this case, it would be natural images. And we have some source distribution, we denote as P. And we typically learn some generator function, denoted as Phi, which transfers between the distribution P to the distribution Q, our target distribution. And today, we're going to talk about a specific family of generative models, which are flow or diffusion models. And in essence, the basic idea here is that the generative modeling is done via a time-dependent process that takes samples from our source distribution at time zero, and transforms this distribution in a time-dependent process up until time 1, which is an arbitrary choice, but that's typically how we do it. We start from 0 is noise, is the source, and 1 is the target. And the function that defines this time-dependent transformation is a neural network that parameterizes the velocity of a point for every time and for every every point in space. So basically, what we have is that we have an initial point x0, and we go along the trajectory that is defined by the velocity field ut. Okay, so ut is our neural network that is learned in flow. In diffusion models, we sometimes learn some other reparameterization of this process. It could be the noise prediction, which is how diffusion models were initially introduced, or it could be the X prediction, which is also known as the denoiser. But what we know today is that we can transform from every each and one of them. So if I have trained the model to learn epsilon prediction or to learn X prediction, I can transform between them and also to the velocity. So we can move along between those. And this is going to be useful for us in some of the applications moving forward. Yes?
Never mind. Sorry.
Okay. By the way, feel free to ask questions I didn't say, but yeah, of course. Okay, so the generative model that we're going to look into today is a flow model, but it could also be a diffusion. So yeah, and that's it. And we said that our model is parameterized by this UT function, which is the neural network. And how do we sample from such models? As I already mentioned, we go along the trajectory that is defined by this velocity field, and typically we use some ordinary differential equation solver. And one of the most known one is the Euler solver, which is a discrete solver, where basically what we do at each step is we compute the velocity where it points, and we take a step in that direction, multiplied by the size of the step, of the discretization step that we have chosen. So this is how sampling would look like. And this brings us to our goal of today, to deal with control generation. So we said we wanted to solve inverse problems, and the tool that we're going to use to define what are the good x's that define our y's, that explain our y's, our observations, are going to come from some distribution that is defined by a generative model. And I like to frame it under the control generation notion. Okay, so what has been done already in this space? We're going to talk about 3 approaches, where the last one is going to be the one that we're taking. But let's talk about a little bit what other people have done. So first way to tackle this is to alter our source distribution. So now what we're going to say is, okay, we want to solve some inverse problem, and we know the operator H, the forward operator, that defines the relation between natural images or whatever distribution that our axes come from. And we can now make a data set of y's, of observations, that correspond to these axes that we have under the given forward operator. So this approach, we will do here is we're going to define a whole new source distribution, and we're going to train a whole new flow or diffusion model to solve our inverse problem task. So the cons about taking this approach are that it requires training, and we will have a problem-specific approach. I mean, for every sort of different inference problems, we're going to have to train another model. This only applies when our forward operator maintains the dimension. What I mean is that, for example, in inpainting, the image remains in the same dimension. But what if I want to solve another type of an inverse problem or control generation? Say that I have some chemical property that I want to generate molecules that satisfy it. Now, my chemical property would be a scalar, and the molecules would be in arbitrary dimension. So this does not apply here. Yes.
Can you maybe use, for example, in painting as an example, and then explain what you mean with changing the source distribution?
Well, okay,
Like,
so here in the bottom, we see an example. Like, okay, I'm gonna go one slide back. So in general diffusion or flow, we train from our source distribution P would be Gaussian noise. And what our model does, it transforms Gaussian noise into natural images, right? Now, in this approach that alters the source distribution, our source is going to be looking, it's very hard that I don't have a cursor. Sorry. So our source distribution would look like images that have these in-painted areas in them. And our model is going to transform from these types of images. So you imagine that your source would have images that are in-painted, okay? This will be the source and not Gaussian noise. And your generation process would look like this. It would denoise only the in-painted area. So that's an example for in-painting. You can imagine any other sort of inverse problem, such as super resolution or blurring, whatever comes in. Is that clear?
sure.
So this first type of approach to alter the source distribution, but as I said, it requires training of a model for every sort of inverse problems that we want to solve. A second type of approach would be to use guided sampling, and here we could think of it as instead of wait, I'm sorry, I'm gonna move the video where I see the videos because it kind of includes part of the presentation. Sorry. So in this type of approach, we can think that instead of altering the source distribution, we're going to kind of change the target distribution into one that is a conditional one. So now we're going to sample from a conditional distribution of X given the observation Y. And the way we achieve this is that we have our prior diffusion or flow model that was trained on our distribution. Say again that it is a model that was trained on natural images. And what we do is that we add some guidance to the generation. So whatever we have this time and space dependent function, gt of X and Y, that modifies our actual generative model in a sense. But the cons about this type of approach, again, that it may, in some cases, require training of a noise-aware classifier or predictor. So this GT of X would have to depend have to make predictions for every timestamp. So it would have to make predictions on noisy images. In other cases where we're using some GT that does not require training, those cases usually know how to handle only the case of a linear forward operator. So our H would be linear, and they often struggle with the noisy case. So is someone is asking a question? Where does the original in-painting image occurs?
I guess now maybe the question is sort of along the lines in this formulation, how would you do in painting?
In the guided setting? Yeah, okay, it's verified. One sec. very hard that I can't use my cursor. So you're seeing everything. Okay, sorry. So in this guided setting, what people usually do is that they modify the sampling from the diffusion model. And what they add is they add some either gradient of a loss between the in-painted image and the denoiser prediction at each step. Because actually, I mean, the denoiser prediction at every step. I don't know if you have ever seen how it looks, but it basically looks at the beginning of the process. It looks like an average image, which would be like kind of a grayish image. And as the generation process progresses, it looks kind of like a less and less blurry version of the image. So it does not contain any Gaussian noise, but it looks like a less and less blurry version of the image. And then we would want our images, our generation process to move along points that resemble the areas that we know about the in-painted image. Does that make sense? I can go and fetch this image that look like that shows how the wizard looks in the process if you want. But...
Am I audible?
Yeah.
Yeah. So I was asking. So basically, you're saying that if I have an embedded image, I'm computing some kind of a loss with the denoise version of the image, and that noise is actually guiding us to the final generation incrementally. So this is what you were saying, right?
Yeah.
Yeah. So in this case, how would we make sure that the original the denoise scheme that we get, it is not actually the embedded version itself?
I'm not sure I understood. Sorry.
How would you? Your talk is not about this. Pardon me for asking about this, but basically, you're if you're taking loss with the embedded image, the bad image that we want to improve. How would we make sure the diffusion image actually does not give the bad image at the end?
I think it's just about having a mask for the loss for the region that you're in painting.
No, okay, I got your question. That's a very good question, and I think that's part of why, like, this is where the generative model comes in, because again, there are two things here. One is that the loss is indeed masked, as Hans mentioned.
Okay.
The loss is only on the known pixels. So we don't want our image to be guided to fill in the blanks with the 0 or with half, whatever value is there. And the second thing is that we use the inductive bias or the information that the generative model brings in to fill it in with a good completion of the image. Does that make sense in a way?
Yes. Thank you very much.
All right, good. Great. So okay, so we mentioned the cons in this approach, and this brings us to the third approach, which is the approach that we're going to take in this work, which is an optimization-based approach. And why would we want to do that? For one, it is applicable to any differentiable h. We're not limited to linear h functions, to linear forward operators. And as I mentioned, for example, if we want to generate a sample that satisfies some, say in molecules that satisfies some chemical property, then our forward operator would not be linear. Our approach also does not require some problem-specific training, and as we showcased in our paper, we can handle the noisy case. So let's introduce Difflow. The setting is as follows. We are giving a pre-trained diffusion model a pre-trained flow model that represents our distribution of the data, the prior distribution that we want to sample x's that explain our observation y. And the way that we're going to solve this is by crafting some loss function, some cost function. For example, if we're talking about some, if it's images, then we're going to have something like this. It will be the application of h on x minus y, L2 distance. But it could be any differentiable function that we want. And basically, this boils down into a very simple optimization problem, except I think, not except, but the thing to notice here is that the x that we plug in here is x of 1, which is the solution of the ordinary differential equation or the endpoint of the generation process starting at x0. So our only parameter in the optimization is going to be x0, which is the initial point of our generation. And sometimes we will also add some regularization to this cost. We're going to see it in the noisy case applications. And let's try to put like the mental image of what happens in this optimization. So we have x naught, which is our initial point. And if we sample it from with our flow model, we're going to get x of 1. All right, and the relation between x of 1 to x0 is the sampling procedure that we chose. And the gradient that we're going to compute is the gradient of our cost function with respect to x0. Okay, so our optimization is going to be with respect to x0. And x0 is going to take a step in that direction. And what's going to happen to x1 is that we're going to solve again our generation process of the flow model up to x1. So x1 does not flow according to the gradient of the cost with respect to x0, but it flows according to the solution of the flow model now from the new x0 that was updated in the gradient direction of the cost. So the algorithm is pretty simple. Again, we have our cost function, we have our pre-trained model, we initialize our x naught, and we iterate over taking optimization steps up to some threshold or designated number of steps that we predefined. And now we're going to discuss the 3 algorithmic choices that we made in the process in making this algorithm. So
how many steps do you actually usually do in practice?
Steps of optimization or
Optimization.
So it depends on the application. I mean, there were applications where we chose to stop by like we defined the stopping criteria by the cost by a threshold of the cost function. So we kind of changed. But I think yeah, it really depends. Like in images, in the images application, we had to take, it was order of 100, I think. For the molecules, I think it was tens, like in order of 10. But yeah, it changed one application.
And how long?
That's something that we're going to have to that we'll also talk about it. I mean, and you were going to ask how long it takes to generate a sample.
Yep, exactly.
So this is, yeah, so this is actually in a sense the disadvantage of this approach, that it's quite costly compared to existing approaches, both guided and if you train a model, because then inference is very cheap. So by having this flexibility and general approach, we lose something which is in runtime. In images, in the noisy case, it would take around, I think it was, again, it depends on the application, but it was around two minutes to generate a sample. In the non-noisy case, it could even reach 10 minutes. And for the molecules, it was around, I think it was also around 2 minutes or so per sample.
Yeah.
But we'll also talk about you know, ways to maybe try to improve that in the end. I see what
Yeah, but
we
I
have
think this is
that.
then very interesting, or like a very important aspect for thinking about the applications where it would be the most useful, maybe. Oh, and we have a little question in the chat. Could you repeat, where does the X1 come from? How do you get the ODE to solve? Well,
Is it true that you solve it for every optimization step? So yeah, okay. I see. I will also have questions before that. Okay, so I'll start with the last one, and then I'm gonna go over them. So yeah, X1 comes from the solution of the ODE. We're going to talk about this step shortly in what we chose. So I'm gonna and yes, it is true. At every optimization step, we have to compute it. How many discretization steps? We're gonna also discuss that soon. And when running optimization, do we use the same xi1 to compute gradient? But if we change it 0, it each yeah, so it changes because we solve again the OD. So xi of 1 is the solution of the ordinary differential equation from x0 of 5. So let's go about the algorithmic choices, and we're going to answer some of the questions that were asked here already. And if something is not clear by then we'll reiterate. Okay, so first, how do we initialize our x0? So I think the natural choice would be to choose x0 as a Gaussian noise, because that's our source distribution, of course. But we did observe that in cases where we have a lot of structural information in our observed signal, in our y, that it was beneficial to use some other initialization scheme, which I'm gonna go over now. So basically what we did, for example, in the in-painting setting, but it also applies for super resolution and deblurring, which were also applications for images that we had. So let's say that this is our observation Y, and we have this masked area in the middle. And what we did is we solved the ODE backward now to the noise. So now we solved from time 1 to time 0 with the in-painted image. So I think this is for me, it was interesting to see that outside of the masked area, the initial point that generates this image actually does look like a Gaussian noise. And I think intuitively the explanation for that, I mean, it's all intuitive and heuristic a little bit maybe, but it is due to us using CNNs, because basically the diffusion model is a convolutional neural network, a unit. So it does preserve some local information. So if we have areas of the image that does look like natural images, the source areas that will produce it would be Gaussian. But we can see that in the middle, it is like kind of smeared. So what we did is we initialized our x0 with a combination, with a blend of some other Gaussian noise with our backward solution from the in-painted image. And we also replaced the area that was smudged in the middle with Gaussian noise. And that really helped convergence and also the performance. So it was a neat trick that was useful, again, only when we have enough of structural information in our observed image, in our observed signal. Now, the second algorithmic choice that we had to make was, which was already asked by our crowd here, is how do we solve the ODE at each step? How many steps we're going to take and what method we're going to use. So in all experiments, we use the midpoint method, ODE solver. It's a pretty simple one off the shelf. I'm not going to go into details about that. And choosing how many steps has a trade-off, because if we take a lot of steps, we're going to have an accurate sample, but it is going to be very memory and time prohibitive to use a lot of steps, because think that, as you already asked, if we use a lot of steps, we're going to have to backprobe through all of these. to compute our gradient of the cost with respect to x0. So there is a trade-off here. In all the image applications, we used 6 steps, 6 function evaluations for the generation. And in the molecule applications, we used 100 function evaluations, which was pretty accurate, which is a already gives pretty accurate solution. And I think the interesting thing here also is that also with very little amount of steps, we were able to get good results on images. So that's also an interesting finding here that we had. And the last thing that we're going to discuss is how do we optimize our algorithm? Which optimizer are we going to use? And the answer is that we used the LBFGS optimizer. And it is simply due to the fact that our optimization here is not stochastic. We don't have, batches or anything like that. We have a deterministic optimization, and we could use this LBFGS algorithm here. We could use the benefits of it. And we also used it with line search, meaning that for every step that we're taking a step that is maybe not guaranteed because it depends on your tolerances, but we're with higher probability going to take a descent direction step. And here we see a comparison to also some attempts that we had with Adam. So the axis here in the plotter, the x-axis is iterations, optimization steps, and the y-axis is the PSNR, which is basically the distance between h of x and y here. Higher is better. And we see that LBFGS performs very much better by a large margin from Adam. This is an averaging of several experiments. And you might say, okay, why don't you take Adam with a higher learning rate? Maybe it will reach the performance of LBFGS. You only went to 0.1 here, and you can see that it goes up every time you increase the learning rate. But what happened with Adam when we took a higher learning rate is that we ended up having these artifacts filling in the in-painted area. So here we also have an in-painted image in the middle, and we were kind of straying away from the flow trajectory with the Adam optimizer. So this concludes our algorithmic choices. Shall I stop and answer questions? I see there's a lot of things happening in the chat, or okay.
Yeah, let's maybe look at this. You've used the NLL regularizer. Could you explain the reasons? Does it have anything to do with solving the boundary conditions of the ODE in equation 9 in your paper? Do you know what's
Okay, so we didn't use NLL regularizer. We actually explained in the paper why it is not a good choice. We can go to the paper and see, oops.
What is NLL log? What is
It's basically a log likelihood regularizer. So yeah, so one thing that
are we supposed to see the paper right now?
Yeah, it's intentional.
We don't.
You don't see the paper?
Yes.
Okay.
We see still the.
Okay, sorry. Okay, I'm gonna share my entire screen. Okay. So yeah, in the paper we do mention the log likelihood regularization. So basically, think that you could take our cost function and add here the log likelihood of the generative model that we have. Okay, so like log p of 1 of x1. You want your sample to have high log probability under your prior, which is given by the generative model. But actually, what happens in high dimensions is that this quantity does not mean much. And as evidence, I mean, we give it here only like one example, but what we see here, so think that this BPD quantity, it's kind of like the log likelihood, but it is normalized in some way. But don't mind the values exactly, but all you need to know is that lower is better. Like lower means a more likely image. And what we see here is that the in-painted image is more likely under our model in terms of the likelihood that it gives back. So this means that this quantity is not a very good regularizer when thinking about generative models in high dimensions. So we did talk about it because it is kind of, it would be some natural choice to go to. But it is good to note that in high dimensions, it's very debatable whether it is useful or not. And I think there's a lot to explore here as well, like research-wise.
Why is that? Like, it seems also right for like all these DPO and our language model fine-tuning. Now we always have that we want to tilt our distribution, and yeah, we don't just want to now completely fine-tune to some reward function. We also still want to stay close to our original distribution and want to sample or still have samples with high likelihood of our original model. And why is that now here so why are the high dimensions here so problematic? But if we, for example, fine-tune diffusion models with DPO, then we also look at that.
So I think also there, but you don't have, like, you do not compute likelihood, right? You do not use this quantity. What you do is you fine-tune with some other data. So you do shift your distribution in a way. I guess what I'm trying to say is that the value of the likelihood does not necessarily represent how likely this image will be in high dimensions. And I think a very, like, the simplest example for that would be, think about Gaussian distribution in high dimensions. Okay, the zero vector would have the highest likelihood. But if you now randomize, I don't know, not infinitely many, but a lot of samples in a very high dimensional Gaussian, if you take samples, you will likely not get this sample, right? Most of your mass would be concentrated around the square root of the sphere. So there are really weird effects happening in high dimensions, which are in a sense break our intuition that we have for lower dimension. So it's I think it's very interesting to explore in general. So that's noting on the likelihood.
Yeah, it's just, I feel like every time something doesn't work, or yeah, every time something doesn't work and we're doing something in high dimensions, we tend to just say, oh yeah, look at all these examples that we've seen in the past where our intuition breaks if we do something in high dimensions. So like, we move on. But yeah, of course, I'm not saying that this now needs to be something that needs to be addressed in your work or so. But we have some more questions that maybe should get to. Let's maybe not do this one. Yeah, if we visualize x0 throughout the optimization, does it become more and more similar to high dimensional Gaussian noise visually? How would you even tell that?
So yeah, we did. I mean, I don't have it in the here in the presentation, but we did look at x0 as optimization goes, and the interesting thing is that it did remain on the manifold, and that brings me to our theoretical result. So maybe let's talk about that, because otherwise I'm not going to finish my talk. So yeah, so the question that, I don't know, that kept me busy working on this was, okay, we're optimizing with respect to this, our parameters are x0, but what happens to x1? Like, in what direction does x1 move when we move x0? Like, we take a step with x0 in the gradient in the direction of the minus the gradient of the cost, but how does x1 change infinitesimally? And we analyzed this gradient. I'm going to put a maybe a little intimidating equation on the board. But I want, maybe I'm not gonna go into a lot of details here, but I want to, to give maybe a bit of intuition. So what, first of all, the direction that that x1 goes when taking a step of x0 is that we go in the direction of the gradient of the cost with respect to x1, and then it is multiplied by the squared Jacobian of x1 with respect to x0. And this kind of projects the direction that x1 goes onto the data manifold. And the way that we can, I mean, I'm only going to give intuition here, but what we see is that this Jacobian term is kind of an integration over the variance of x1 given xt. Now, this random variable, x1 given xt, its expectation is the denoiser function, is the denoiser that we learned in also in diffusion. But the variance of this random variable, the way that it behaves is that at time 0, it is the variance of the data, actually. And as we move along in the generation process, this is going to be the variance is going to be getting smaller and smaller, because at the end of the generation, we're reaching like kind of something x1 given xt is going to be something that's going to be very concentrated around x1. So we can think of it like in the beginning, we have this projection on the principal components of the data. And empirically, what we did is we took an example with our example here is that we have an image that was that we in-painted and we took away 90% of its pixels, so that's a distorted image. We initialized our algorithm with some x0, and this is the initial x1 that corresponds to this x0. And what we have here is the visualization of x1 and not of x0. But what we see is that x1 does kind of remain on the data manifold. So we don't see like some linear interpolation between the initial point and the end point. We do see changing across along some very different along different birds on the way. For example, the initial bird and the end bird does not have this triangle shaped, like it has this triangle shaped head. And in step 4, I think, and also in step 6, we see that we go through some bird that has this triangle shaped head. And I looked into this species of birds in this class of ImageNet. And actually there exists some, it's called the Himalayan bubble, and it does have this triangular shaped head. So in a sense, we move on the data manifold as we optimize. So I think that's a very nice example of the dynamics of this optimization, which are injected by this optimization through the generation process.
Okay, so essentially what we're saying is, right, the x1s that we generate while we optimize also the x0, the x1s are still something that could come from our distribution, and this
and
kind of
correspondingly the x0 will be looking like a Gaussian. Yeah. I
yeah.
didn't visualize it here, but we did look at it in the and use. I mean, we also monitored the norm of x0 as we go away, and it kind of remains around square root of d, which is where most of the mass is concentrated in Gaussian noise in high dimensions. So it has a very nice behavior, like in dynamics.
Okay. But yeah, this intuition very much makes sense, right? That our x1s still look like samples from our flow. Well, yeah, they're samples from our flow.
Yeah, but your x0 could have, drifted away to be x0 that does not look like a Gaussian, and then your x1s would drift away from the distribution. And it does not happen.
Is that actually the case? Like if you let's say sample something from the mean, or not sample something from the mean, you just take the mean and put it into your the all zeros and put it into your flow. Will this not be a sample from the
No,
Okay.
if you put in a null zero vector, a null zero image and try to generate from a flow model, you will get, I think you will remain around 0. Like, it's not a likely sample.
Okay.
Yeah.
Good.
Okay. So let's talk a little bit about the experiments. We don't have a lot of time. Okay. So we're first going to talk about linear inverse problems. And the setting here is that we had a class conditional flow matching model trained on ImageNet 128. And the tasks that we considered were super resolution, in-painting, and deblurring. And our H, our forward operator was here linear in all these tasks. And we can see that our method reaches either state of the art or is on par with all these the other approaches. The other approaches are the PyGDM and OTOD are guided flows, and Rediff is kind of like something between an optimization-based approach and guided flow. And this is kind of validates that our approach can perform as well or even better than state-of-the-art approaches, although it is slower. And we see here some examples. And also we tried it for the noisy case, where here we modified our a bit. We did add some regularization. Sorry. We did add some. We did need to add some regularization. So one thing that really helped here was to early stop the optimization at the noise PSNR, because think that if we let our optimization go without stopping, it would also fit the noise. I mean, you could find an X0 that generates the noisy image because our models are invertible. So stopping it at a noise PSNR is very useful. And the second thing is that we regularized X0 to remain on the square root of the sphere, which also helped in the noisy case. Yeah, so that's it about the linear inverse problems. And the second type of applications that we showcased our method on were nonlinear inverse problems. And this is kind of the advantage of our approach compared to all these guided flow approaches that only handle the linear case. So the example that we used for a nonlinear inverse problem were having a latent diffusion model or latent flow model. So the flow happens in the latent space, and then we have the decoder applied to our result of the flow. So now our forward operator is not going to be linear anymore, and this is a case which does not apply for those guided flows approaches. And we showcase that on text to image and text to audio with very large models. And results are in the paper. I'm not going to go into this, I think, because I want to talk about our last application, which has very nice observations, I think, and interesting questions for the future. So in the conditional molecule generation setting, what we had was a pre-trained unconditional diffusion model, actually, on the QM9 dataset. And I want you to remember that we said that we could transform from noise prediction to flow. So this is where we use this. And the task that we wanted to solve here was property prediction. So we had a property predictor, and this was our forward operator, or H. And this was a neural network that was trained to predict the properties. And you can see here that we have been able to beat the state-of-the-art by a large margin. What we see here in the table are that we have 6 chemical properties. And the numbers in the table are the mean absolute error values from the target. Okay, so the setting is that we give a target value of the property, we generate with the model or with our optimization, and then we compute the gap in the generate between the generated and the target value, where the value of the generated sample is computed with the property predictor.
How
Yeah.
did the other people do the conditioning or ensure that they
Yeah, so
generate?
I'm gonna talk about it right now. So these three models above were actually conditionally trained models. So they were diffusion models that were conditionally trained to generate samples for a given property. Now, in general, also I think in images, conditional models typically beat these types of approaches. So like training a conditional model would perform better than optimizing or than using a guided flow. And here we observe a gap in the ability to learn conditional models in the domain of molecules, which I think it is very interesting because there is some gap here to be filled in conditional generation for molecules, at least in these types of models here. And I think our approach also enables some very interesting applications where we could support a multi-condition or soft controls, like you could condition on multiple properties and generate for all of them, have a cost crafted for like, you know, have a distance from the alpha property and also from the delta epsilon and satisfy both of them. We could also explore different initializations, say initializer X0 from a desired molecule and then start the optimization from there and maybe find a molecule that in a sense is close to our initial one that satisfies some property. This could also be very interesting to utilize our approach for. And in general, we can look at D-Flow's optimization gradients to have a better understanding of how the conditioning happens in these models. So yeah, so some conclusions. We have established a robust optimization scheme for controlled generation from flows. I think I didn't mention it, but basically the algorithm that I presented and the algorithmic choices that I presented to you transferred from along all these applications with very little change. I mean, the optimization scheme and everything, or all the hyperparameters remain pretty much the same. And this shows how robust this pretty much. It was for different models, different data domains, and I think that's very nice. Our experiments reveal a very interesting gap in the ability to learn conditional models on molecules. And the question is, what are the possible improvements? Is it something that has to do with the architectures, with the data, with our ability to learn on these data domains? So I think this is also very interesting to understand. We do have limitations. Our method is slow in write times compared to other methods, but for example, in molecules, there is no other efficient approach that beats our approach. So currently, this is the best that we have. And we do a per sample optimization. And if it's costly, then it is a disadvantage in a sense. And interesting future directions and improving this would be to maybe use faster solvers to reduce the number of steps and improve the speed of our optimization. And for the linear inverse problems, we could think of combining these guided flows approach and maybe improve them by also adding an initial point optimization. So think that we're gonna use the guided flow, which is gonna put us in a kind of good place already, and then only take a few optimization steps to tune what we get. And this would not be very costly in terms of runtime and might be state of the art, which is also interesting to look into. So thank you. I'm just gonna, I want to thank my my collaborators on this paper. It wouldn't have happened without them. So yeah, that's it. We can have a few questions.
Okay, then right, you sort of now have an approach for optimizing stuff that's or you don't just sample your generative model or just sample it conditionally. No, you have a sample and that's sort of needs to be somewhat good already, and then you optimize it on this data manifold to get somewhere. And now if we have discrete data, then we've, for example, for protein sequence, there we've often seen the case that the approaches that work the best for actually sampling good sequences is by starting with a sequence that's already good and then optimizing it further with something like MCMC instead of just sampling many new instances or many new samples from maybe also a conditioned generative model. And do you think there's like maybe for using your method for optimizing other objects, we could do something like putting or taking a sample and evaluating your flow backward. So we have it in your latent space and then or in your Gaussian, and then optimizing it with your procedure in the Gaussian.
Yeah, so I think that's actually I'm not sure exactly how it is done
So
in like
we
proteins, but how do you sample when it is discrete? Do you still or do you at each step generate like a transition matrix and then you sample from this
So
distribution
for
or
something like this, it would probably not work right where we have these like diffusion models or flow models that inject discrete noise. But if we have something just where a diffusion model that operates in continuous space, a flow model that operates in continuous space but still generates some a discrete sequence, or let's just talk about continuous data itself, then we could maybe evaluate the flow backward and put the sample
yeah,
into
of
Gaussian
course.
space.
I think
And
it's worth trying it for every type of flow or diffusion model that you have, you could apply this method. I don't think that like there's a like a limitation here in that sense.
yeah,
I mean, I'm not sure what will happen, like you said about when you have these discrete data, but um, but eventually, if you have when your data is discrete, you do have some projection, right, in the end of the generation process. So
yeah,
yeah, so like the neighborhood of the discrete point would still point towards this discrete point, right? So in a sense, I think it's like images, right? Also, images are essentially discrete creatures, right? That we smooth out because we have pixels in bytes. So I think it's worth looking into. Yeah, definitely.
I was just thinking what could be applications here, because I think the molecule application that you show here already, maybe I don't know how practical it actually would be. Right? We not, or I don't know anyone at least who is interested in generating molecules that have a certain, just generate any type of molecule. I don't care what molecule it is, as long as it has this and that homo-lumo gap. Yeah, but maybe there are some other
Yeah,
molecule
so
properties.
I think maybe specifically these properties in the QMNI may not be
Yeah,
interesting for people, but I'm not the domain expert in these areas, but maybe for cases like I don't know, you look for some molecule that binds good with some protein and you know about some properties that these molecules should satisfy, and you could guide it towards having these properties. I'm not sure which are, but
right. And here you're already pointing out one property, or you're bringing us in the direction of one property that people certainly are interested in a lot, and that is designing, right? You could take your diffusion model or your flow model that's maybe even also conditioned on your binding pocket, which you want to generate a small molecule for. And now if you have this flow model, you could then have some value function that tells you how much, hopefully some differentiable function that tells you how strong your molecule binds to, or some energy function or some force field that people use. And I guess this is also something that I've been talking about a little bit with Yaron, right? If you have your energy function, then it will be very stiff, and it will be a very rugged loss landscape, so to say, or energy landscape. And now, yeah, maybe it would make sense to try to optimize whatever we generate as binding to the protein with p-flow, or first sample something sample something conditioned on the pocket, and then optimize it more toward the towards some energy function with d-flow.
Yeah, this
So
could definitely be
that I
interesting.
would find very cool if someone in the chat tries it. But we have another question from Denise.
Okay, so I think that's gonna be the last question that I'm gonna be able to take because I need to go. So Denise, go ahead.
Sounds good.
Yes, hello. Thank you. So I just wanted to ask if, well, this is kind of a broad question, but I would say, can this be applied not just to a discrete problem, the one that Hannes discussed, but actually to problem that tries to learn some symbolic algorithm, basically. So essentially solving the inverse problem for something like a group structure, something like that. It's just theoretically, because I just want to understand the H function that you're using for your L, how complex can it be? And essentially, like, can you try to recover some very particular, like, sparse structure from your, like, sparse sampling? Maybe it's a bit abstract, but hopefully, in general, my question is sort of to limitations on solving some like really strongly conditioned inverse problems where there is very sparse, like very complete structure, and you only have a sparse sampling for it.
So I think an example for a sparse sample that we had was the example with the bird where we had very few samples. I'm not sure it like here. So this was our Y, this was our observation.
Yes, that's why I asked this. But still, in this example, you can generate many birds for this particular structure, right?
Yeah,
but
so we did manage to generate a bird that does look quite close to the ground truth image, yeah. So I'm not sure how it will apply to other domains, and but I think it's very much worth exploring.